Welcome back. This lesson we're going to be looking at the second derivative. So we've looked at all the shortcuts and the different rules for finding the derivative. To find the second derivative, we just have to derive our answer when we're finding the derivative. So let's start with a function, and I'll do two examples in the two different types of notation. So let's say we had f of x equals 2x cubed minus 5x squared plus 7. So to find the derivative, we'd write it as f dash of x, and we take the power, multiply it by the coefficient out the front for each of the terms. So 3 times 2 would be 6, and then the power for that x drops down by 1, so that'd be 6x squared. The next one would be 2 times minus 5 is minus 10x to the power of 1, and then the 7 would drop off because that was 7x to the power of 0. Then 0 times 7 is going to be 0, so it doesn't matter what the power of x is, it'll disappear. So any constants, when we find the derivative, will drop off. Rather than the power of 1, we just write it like that. So the second derivative is just to repeat the process. So this time we'd write f with 2 dashes to show that we're finding the second derivative. And then we just repeat the process. So 2 times 6 would be 12, and we have 12x, and then negative 10x to the power of 1. 1 times negative 10 would be negative 10. X power 0 is 1, so the x drops off. So that is our second derivative. We can do the same thing if we have an equation for y in terms of x. We'd say y equals, let's make up another one, let's say minus 7 x to the power of 5 plus 4x squared minus 3. And our first notation would use dy dx, so the change in y over the change in x, equals negative 7 times 5 is negative 35. X to the power of 4 would drop down by 1. 2 times 4 would give us plus 8 x to the power of 1, and the minus 3 would drop off. Now, when we're doing the second derivative, our notation changes to d squared y over dx squared. And then we just follow the same process. So we'd derive our derivative. So 4 times 35 would give us 140, hopefully, and make that a negative. X cubed, and then we have plus 8 is our second derivative. Okay, so it's all the same skills you've used. I've picked two nice easy examples. We've just got terms separated by pluses or minuses. But for some of them, you might have to use a chain rule, the product rule. If I'm feeling extra mean, maybe the quotient rule. But why do we do this? We'll look at the derivative is finding us the change of the original equation, so the gradient at any given point for the tangent, or the gradient of the tangent at any point for the original equation. Then when we graph the derivative, we're doing the same thing with the second derivative. We can find the gradient of the tangent at any point along the graph of the derivative. So we're finding, well, how fast is it actually changing the amount it's changing of the original function? And you go, well, now you're just making things harder than they need to be. But for those that have maybe done some physics, or later in this topic when we get to kinematics, we'll look at things like position versus time, and then what that changes, how you change position over time is your velocity, and how much you change your velocity over time would be your acceleration. So when we're trying to go from an equation for the position to velocity to the acceleration, we're actually finding the first and second derivatives. So we'll put these into practice, but for now we're just going to practice doing the skills and then do some applications later in the topic. All right, all the best for the second derivative.